Hi, this is Jong-un Kim. I'm attending PhD in Yonsei University and main author of this paper. I'm going to be presenting to you today about do topological characteristics help in knowledge distillation. Knowledge distillation is a leading approach in the field of model compression. Its purpose is to enhance the performance of a smaller network, known as the student, by sharing knowledge from a larger, well-trained network referred to as the teacher. The crucial aspect of knowledge distillation is deciding what knowledge from the teacher to transfer. Initially, a method known as vanilla KD, introduced by Hinton, used the teacher network's soft logits as the knowledge. To better mimic the teacher network, feature-based knowledge distillation methods were developed that imitate the internal feature representations. Among various types of KD methods, the most relevant to our work is relation-based KD. The relation-based KD method are introduced to identify intricate relationships across embedding features. They define relationships as similarity measures between distinct embedding features or assessing the structure between two or three pairs of embedding features within the latent space. These methods teach the model the full relationship via interactions between a few embedding features. However, relying on partial information to understand the entire structure is limited. Therefore, transferable knowledge that teaches the broader context of relationships between all embedding features should be defined. However, it is difficult to consider all arbitrarily multiple relationships of the features simultaneously. To tackle this issue, we chose to use persistent homology, a primary method in topological data analysis that gauges the topological features of data across various scales. As it embeds comprehensive structural information like distribution shape and multi-scale structure, persistent homology can grasp the global topology of data. There are several visualization methods for persistent homology, including persistence diagrams, Betty curves, and persistent landscapes. In this case, we have opted for persistence diagrams, which depict the inception and cessation of topological features with precision. Previous studies have explored the integration of persistence diagrams into deep neural networks for geometric data analysis. However, these studies have limited their numerical experiments to domain-specific datasets, and persistence homology has only been used to extract information to augment the input data for the network. In contrast, this study takes a step further by directly leveraging the topology as knowledge. Now, I will explain the background of persistent homology and persistence diagrams, among other things. The goal of topological data analysis, TDA, is to infer the shape and structure of the underlying space that generates the data points. This is achieved by analyzing and calculating the topological characteristics of the data, such as connected components, loops, and voids, which persist through continuous transformations. One important topological characteristic is the k-dimensional hole. As shown in the figure, a hole remains invariant under continuous transformation. We can compute the number of k-dimensional holes in a topological space by calculating the rank of the k-dimensional homology group. Persistent homology computes the creation and destruction of these k-dimensional holes by exploring the spaces across different scales. The persistence diagram then visualizes the computed persistent homology. Here, typical pipeline for using persistent homology as an input of neural network. First, convert a point cloud into a simplicial complex, which is a topological space where the homology group can be computed. Second, we construct a nested sequence of simplicial complexes, which is called a filtration. Then, we can summarize the birth and death of k-dimensional holes with respect to the filtration and summarize into the form of a persistence diagram. Finally, we vectorize the persistence diagram to feed it to a neural network. I'm going to explain this step by step. Before understanding the concept of a simplicial complex, it's essential to first know what a simplex is. A simplex is a generalization of the notion of a k-dimensional triangle. For example, a zero-dimensional simplex is a vertex, a one-dimensional simplex is an edge, a two-dimensional simplex is a triangle, and three-dimensional simplex is a tetrahedron, and so forth. Then, a simplicial complex is a set of simplices that have the following good conditions. You can think a simplicial complex is a topological space that approximates the underlying topological spaces where data points come from. The typical method to construct a simplicial complex from a point cloud is via torus-RIPS complex. To construct a RIPS complex, we begin by considering a set of balls with a radius r centered at each point in the point cloud. Each point is considered a vertex in the RIPS complex. We then connect two vertices with an edge if the distance between them is less than or equal to 2r, which indicates that the balls centered at these points overlap. For higher dimensional simplices, we form a K-simplex if every pair of vertices in the set of K plus 1 vertices is connected by an edge. This means that the distance between any 2 points in the set is less than or equal to 2r. By varying the radius r, we can construct filtration of RIPS complexes, allowing us to capture topological features that persist across these scales. Persistent homology then helps us analyze these features by tracking their creation and destruction as r changes. A filtration is a nested sequence of simplicial complexes. We can construct a RIPS filtration by increasing radius from -infinity to infinity. A persistent homology is a method that analyzes the creation and destruction of k-dimensional holes over filtrations. For this example, we can identify two loops by computing one-dimensional persistent homology. These loops are distinguished based on their persistence, which is calculated as the difference between their death time and birth time. A k-dimensional persistence diagram visualizes the results of computed persistent homology. It is defined as a multi-set of pairs of birth and death times for all k-dimensional holes. For example, here all one-dimensional circles may initially appear at similar times. However, larger circles, like alpha-1 and beta-1, persist longer than smaller ones, such as alpha-2 and beta-2, which disappear earlier. Persistence image is a vectorization method of persistence diagram. It converts the persistence diagram into an image representation where each pixel's value reflects a weighted combination of points from the persistence diagram, determined by their persistence and density of points in persistence diagram. This transformation enables complex topological information to be structured into a format conducive to machine learning analysis. By leveraging persistence image, networks can capture the comprehensive topology of point clouds, facilitating tasks based on the geometric and topological attributes of the data. In this section, I'm going to introduce our methodology, named TopKD, and revisit the conventional KD. Given pre-trained teacher, T, and student, S, each model consists of a featurizer and classifier. For the teacher model, the output of any layer of the featurizer for a training sample xi is represented as ftxi, and the pre-activated output of the classifier is indicated as ztxi. Similarly, the outputs of the featurizer and classifier of the student network are expressed as fsxi and zsxi, respectively. Then, the student model for image classification is trained by minimizing the cross-entropy loss. In vanilla KD, the KD loss function is a Kullback-Leibler divergence designed to minimize the soft logits of the teacher and student. Our proposed model, TopKD, consists of two stages: pre-training RIPSnet and training student network. In here, we designed to transfer the persistence diagram of teacher embedding features as knowledge and define this as the global topology knowledge. Furthermore, for effective integration of persistence diagrams, we use the persistence images as a vectorization, which can be strengthened the global features by steering the influence of persistence. Computing persistence diagrams or persistence images at each learning iteration requires significant computational resources. To address this, we use RIPSnet to approximate the persistence images of the teacher network's embedding features in the first stage. We generate point cloud data from the teacher network's embedding features and use the GUDI library to calculate their corresponding persistence diagram. When the training is completed, RIPSnet is frozen during the training of the student network to approximate persistence images of the embedding features from the teacher and student networks. To enable the student to mimic persistence images of the teacher, we define the topology distillation loss function. The L2 norm was chosen because persistence images are elements of Rn, and the most natural metric in this context is the Euclidean distance. If the channel dimensions are differ, a 1-by-1 convolution is applied to student embedding features. The logits represent high-level task-relevant knowledge, therefore, to use it further, we define the final loss function for top KD by combining the vanilla KD loss with the topology distillation loss. Next, I'll introduce our experiment results. Consistent with previous studies, we compare top KD with representative KD models for each distillation mechanism. Table 1 presents the accuracy for pairs when the teacher and student networks have the same structures on CIFAR 100. For a fair comparison, we followed the experimental settings for CRD, as in previous studies, and compared the current results with the values specified in paper. Top KD surpasses both the student model and vanilla KD by a large margin, demonstrating the effectiveness of using the global topology as knowledge. In addition, top KD displays competitive results compared to other representative models of existing KD mechanisms. These results highlight the potential of top KD. Notably, top KD mimics the PD that includes information on the similarity, distance, and distribution between embedding features, outperforms CC, SP, RKD, PKT, and FSP, which mimic only fragmented information. We also conducted experiments with teacher-student pairs that have different structures. Table 2 shows results consistent with those in Table 1. We evaluate the proposed method on the ImageNet 1K validation set to demonstrate its effectiveness on a large-scale dataset. Similar to the previous experimental setup, Tables 3 and 4 reveal top 1 and top 5 accuracy when the teacher and student structures are homogeneous and heterogeneous, respectively. We want to emphasize that top KD outperforms other baselines in top 1 accuracy. Furthermore, top KD also surpasses the teacher's top 1 performance. We carry out ablation studies to examine performance in relation to the dimension of PD, the number of points in point cloud data, and the optimal stages for top KD. Additionally, to demonstrate its generalizability, we have also applied top KD to other tasks involving transfer learning and object detection. For a deeper understanding of top KD's potential, please refer to our paper. To verify the topology distillation loss, we demonstrate how matching the approximated persistence images for the embedding features of the teacher and student networks affects the actual distance between their exact persistence images. In the upper bound, the second term represents the topological distillation loss, and the first and last terms on the right-hand side represent the approximation errors for the teacher and the student, respectively. Thus, the approximation capability is crucial for matching the exact PI of the student to that of the teacher network. However, the last term is not directly minimized throughout the training process of the student. We evaluate the approximation errors on the embedding features of the student and teacher networks. In table, our method has smaller errors compared to the students trained from scratch or with KD. This effectively tightens the upper bound in previous equation. Since RIPSNet is trained on the embedding features of the teacher network, it produces more accurate approximations for embedding features with a similar structure to the teacher. Thus, we conjecture that the smaller errors observed in top KD suggest that our method produces embedding features more closely aligned with the teacher network than other student networks. When visualizing the exact and approximated persistence images of zero-dimension homology, we notice that top KD generates more realistic PIs than other methods. Despite this, the persistence images produced by all student networks seem almost identical. We suspect that this lack of variability in the approximated persistence images stems from the difference in the scale of embedding features between the teacher and student networks. We use UMAP to visualize classification results. The teacher model shows well-defined class clustering, indicating an organized latent space conducive to high performance. However, top KD organizes points by class more effectively than vanilla KD, creating clearer distinctions between classes like beaver, bee, aquarium fish, bear, and beetle. Additional visualization results and quantitative analysis of the UMAP is provided in the appendix. This is the end of my presentation. Thank you.